Started. Um, I hope you all saw the first assignment that I posted 2 days ago. In case, because the labels of those assignments, those binary labels, are sort of integers, right? So basically, you've been asked to do a regression for a classification problem. If that makes it hard for you to visualize or just think about the problem as it is, I mean, I don't care if you prefer just to add another column, say price, and then generate some floating numbers for yourself, like non-integers. If that makes it easy for you, if it's fine the way it is, just use those classes of 1 and 2 for the name of the binaries, okay? Because I'm not gonna just judge or your TA wouldn't be grading based on the specific numbers of your output. We just want to make sure that you know the process and you're using your various tools in order to come up with a solution, okay? And there is no single solution that is correct in machine learning. In most of the cases, there are like many. Okay, all good? Okay. All right, so today we're going to talk about gradient descent. Let's just recap what we have been talking about in the past lectures. So we started with the linear model, linear classification, and regression. So we jumped towards logistic regression, and then we mentioned that we use a theta of S in order to soft threshold using this formula, e to the raise of S divided by 1 plus E of S, to sort of have a soft threshold over our incoming signals, right? Okay, and that makes it more interesting for us because we could play with the probabilities. Playing with those, we entered the world of log losses and cross entropies and so on and so forth, which we talked last lecture. So basically, we could compute the loss function En of W as the summation over all of your n points of a log loss function, and that was your output of your S actually. So we talked about the fact that in logistic regression, more importantly, a regulated version would be beneficial. So that's why you see those regularizers with a W, right? And just like the linear regression, the function of f is a convex function. So it opened us more opportunity to tackle the solution. So we reached to the point that we thought, okay, instead of using least squares method in order to solve the logistic regression, and since because this is not a closed form solution, how are we going to tackle this, right? There is no closed solution because it's not a linear solution. And then we talked about we need to focus on iterative methods, or say we approximate the results. And one way to do that was gradient descent. So today we're going to talk about how we're going to implement a gradient descent and how we're going to use it. Okay? All right. So basically, if you want to formalize what we want to do is we want to minimize the function f for those x's in R, in n-dimensional R, with an unconstrained minimization, okay? So it's a global minimization. So typically your f function is differentiable in x. It should be, because we need to compute the gradients. But as we know, a closed form solution is not may not exist. So we're going to use some numerical approaches, such as one of the famous one is gradient descent. Okay. All right. Okay. So before starting that, let's just have a quick example of computing a loss function for logistic regression. So say you have 2 points, or 2 set of points, let's say. So here and here. The class of the right one is +1, the other one is -1, okay? And you have used two hypotheses, so two linear classifiers, okay? L1 and L2. As you see, it's obvious that L1 is x equal to 0, right? And L2 is x1 equal to 0. So it's going to separate this space, and the other one separates this space, okay? And 2 points we have is like here, +1 and 10. The other one is -1. It's -1 and -10. So it's 10 actually, -10. I hope you can see it. So what we have here as an example, we just showed 1 point. It could be a vector of point or many data points, just for simplicity, okay? So your x1 is, let's call it epsilon and 10. You just show that it's marginally on the positive domain, so on the right side. And x2 is minus epsilon and 10, so it just shows that it's marginally on the negative side. All right? And the classes are, for this, x1 is +1, which is this, and for 2 is -1. Okay? So that's the question. The question is, using these two lines, two hypotheses, L1 and L2, which you can easily see here, L2 is actually on top of x1, and L1 is on top of x2. What's going to be the loss of using a perceptron, a linear classifier, or later, what's going to be the difference in the loss function of a logistic regression? Okay, so can anyone just quickly mention what's the loss of using a linear classifier for this, either of these two lines? So what if I use L2, okay, to separate these two? What's the loss here? Say I'm using a perceptron. So you have these 2 points. This is plus. Say this is a star. This is cross. You have this classifier. What's the loss here? Yeah. The classification is perfect, right? It classifies those classes with no issue. Okay? So this line can easily classify these 2 points because one of them is +1, the other one is -1, right? So this line classifies correctly. So the loss function brings the output of 0. How about L1 here? It's the same, right? So both way, if we use a linear classifier such as an L1 or L2 here, both case we have a perfect classification. So on both cases, the En for pointwise is going to return 0, right? So in sample error of W1 and in sample error of W2, using these two W's for each of the lines, is going to bring 0 because the classification is correct. We don't have any misclassified point. Okay? So now let's see if we use a logistic regression, what's going to be the output. You recall that for computing the En or the capital En or the in-sample error, we had to use this, right? Let's just expand it using the numbers we have. So x1 and x2 we have, and also we have the W's for the L1 and L2, right? Let's see what's going to be the output of the loss function for logistic regression. So that was the formula that I just mentioned. So we want to compute the in-sample error of W1, which is corresponding to the L1 line. So it's equal, so we have 2 points, 1/2 log of 1 plus E minus W1 Tx. So that was for the case of -1 class, and this is the class for the second class, right? That's why this is positive, this is negative. If you compute this using the epsilon that was given, the output of in-sample error of W1 becomes around 0.69. So I'm just trying to write it here. 69. Okay? Now we're going to do the same for the line W2. So in-sample error of W2 becomes, again, 1 over 2 of the class of minus and plus. So you see the output here is now much, much smaller, right? So using a logistic regression, we can find that W2 is clearly preferred over W1. Whereas if we were using a linear classifier, on both cases, it would be equally good to us. Okay, so that's why you understand in logistic regression, normally, if we have more flexibility, it'll give us more information about a type of hypothesis we were using. And depending on the problem, it's more flexible. Thus, it yields more challenges. And one of them is just we're going to see today because we are trying to solve it and there is no closed form solution. Okay, is it clear up to now? Okay, so what if we consider another W2 with a new different set of weights? Now instead of 1, what if we had W2 as 0, 0, and 100 here? What would have happened? Right? It would be still the same line, but the loss function would be much, much smaller. So now we got a dilemma. How are we gonna tune this, right? Because now, even in logistic regression, different W's are giving us the same loss output, right? A little bit smaller. How are we gonna tackle this? How are we gonna tune this kind of situation? Is again, we come back to the regularization for logistic regression. Now we can add another hyperparameter to play around with the W and regularize that in different scenarios. So that's another example that we can regulate the output in a machine learning model. And how we're going to find find the optimal value? One way is just you iteratively in a loop or exhaustively just search a range of number, or in a cross-validation mode, you can play around and cross-validate this using different training and test set. Okay. All right. So now let's start talking about the gradient descent. We have an unknown function of f, right? We are interested in finding the optimal spot in order to minimize the loss function, right? So we call that x star. So in order to find, when we have such a function between a range of x1 and x2, and we're interested in defining the behavior of a point such as x star, if we use derivation of f over d of x, normally we have 3 options, right? If the chosen x, so say we chose our x here on top of x star. If that was the case, and x was here, right? if the f prime of x turn out to be 0, it shows that f of x at this point, which was x star, is minimum, right? So you can just see that the f prime is 0 at this point, and it shows that x, which was on top of x plus x star at this point, is minimum. If I pick my x's this range, thus my x is greater than x star, definitely the f prime has a positive slope, thus it's greater than 0, thus it shows that f of x is decreasing, right? On the other hand, if you use it here, it's obvious that f prime of x is smaller than 0, thus it shows that f of x is decreasing. So using this three basic algebra, we can start expanding on how we're going to tackle gradient descent, right? So in general, we are starting somewhere. Say this is your f function, right? Say we are starting here. This is not a good solution in that three-dimensional paraboloid, right? If you just, we are starting to reach here, and here in this function is here, right? That's our optimal point we want to reach here. So we need to carefully choose and go in a loop, step by step, and then see if we are going towards the right direction, if we are descending, right, our function. There are so many other cases that we get stuck somewhere in a saddle point, in a multiple stationary point, so I'll talk about it later. But for now, let's just assume that you have a monotonic function, such as this, you start either way, and you're interested in finding, going step by step towards the global minima. Okay, let's just have a look at a quick animation of gradient descent. So say after 50 iteration, so we started from here, and then we gradually descend towards the global minima here. Okay, so that's the whole point. It's just as if you just roll a ball and it's going to descend down the hill up until a point it stops. Okay, now there is another hyperparameter here, and that's the step size, right? What's going to be the step size of us in each iteration? The other one, what's the direction? Because we are talking about the vector space. What's going to be the direction? Are we going this way or that way? Right? So we need to find these two first before defining gradient descent. All right? So now, say this is our function f of x. So we're starting here, x0, and we are trying to go towards our x star. Okay? This blue line shows our step size, right? Here, for instance, we picked a bigger step size. Here we were trying to understand that, okay, the slope is changing. If we don't decrease the step size, we might overshoot our local minima, right? So if I just carry on this way, I'm just going to pass this and arrive here. Then I have to come back again, right? Now the question is how I'm going to change this adaptively, right? Do I have to start big and then go smaller and smaller? Do I have to make it adaptive? Do I have to have another model to just guide me on that? So these are different things that we need to consider when we apply gradient descent. But first of all, let's just formalize what we have so far. So in a high-level manner, the gradient descent starts as to, you're going to initialize your x0 where to start, right? to start from here, for instance, we start from this. And then we're gonna have three different scenarios. If f of x, if prime of x was approximately 0, so close enough to 0, we are almost know that, you know, we're almost sure that we are somewhere in a minima, either a global minima or a local minima, okay? If not, if this slope was positive, then it shows that we have to carry on. We've already overshoot it, okay? So we are going back uphill because the slope is positive. So we need to deduct our, so this is step size, epsilon, okay? We need to go back here. So perhaps we are arriving here, then we need to come back, right, with the step size. Otherwise, if the slope is still decreasing, so we need to add that step size and just carry on going in a loop, right, up until we either reach a stop point or we might have overshooted the solution, okay? Let's, yeah.
I have a quick question. So for number 4, is it because the step size is too small?
Either the step size was too small or we were in our first iteration, perhaps. Right? So, so far we haven't talked about the size of epsilon. Just consider it as a variable for now. Okay. All right. So this is a step size. Let me just get rid of this. So these are step size. Small is going to be small. If you take it very small, your progression would be very, very slow. If you pick it large, you might just jump over the, say if you take it super large, you're just going to jump back and forth right here. You're not going to go anywhere, right? And forever you're going to stuck here. If you pick it very small, it's going to take you forever just to come down here. So these are different, you know, caveats. Yeah, question?
Are we just trying to find a local minimum or a global minimum? Or right now,
We would love to find a global minima if it is findable, but not all the functions are this sweet for us. Let's say. I'll describe some other scenarios that we are not able to find a global minima using gradient descent, and there are some other methods you can tackle. Okay, a good question. Question?
Wouldn't it be a good strategy to take big steps first and then keep on reducing it?
Yeah, actually, this in practice, most of the machine learning models are having this type of behavior, so we can define it. There are so many other hyperparameters. So step size is generally known as learning rate, right? But we have other hyperparameters to affect that learning rate. So you start small, go further, or just start big and then go small. So yeah, there are so many different ways you can tackle it. You know, these are numerical approaches, and machine learning is normally falling into that. So there's, by just tweaking a little bit, you're gonna have a different result, right?
and also there's like some calculation for the initial point. Like there is some mathematical formula.
Yeah, sure, yeah. In many of the algorithms, they just say initialize it to a random number, and then start training. So because actually each of those steps is one step of your training, right? Say you are training a neural network or a logistic regression. So you start with a high loss, like, I don't know, 5.5, and then you gradually decrease it to, like, I don't know, 0.25. And then you see that after a million more iterations, I'm not gonna find a better spot. Let's just stop here. It's good enough for me. Okay. Okay. So, in general census is like we initially start epsilon with a large number, so descent becomes faster, and later we can just make it smaller and smaller. This will help us in general to to avoid overshooting. Say we are interested in running it on k iteration. So each of those E of k would be 1 over k, okay? Now, we talked about step size a little bit. Let's talk about the direction. How are we going to find the direction to which we need to guide the algorithm to go, okay? So if we have a look at it again as a vector value function or in a vector space, so that paraboloid of this solution here, so you have two features, and as your f of x1 and x2, you start somewhere here on a surface, outer surface, and you're interested in coming to the global minima, right? So if you project that to your hyperplane of your features, it's as if you're starting from x0, right, on a 2D space, and then you're going this way now towards your x1 and then finally x star, right? You're going this way. How am I going to find this direction? That's the job of my unit vector u, right? How large of u I'm going to go for? That's why you multiply epsilon to that. So epsilon u will give you both the value of the step and the direction of the step towards the x star, right? So in general, we can say given x0, right, the starting point, we need to take these steps. We need to update our x plus epsilon u, right, the vector of u. And actually this one, the vector of u shows us the spatial direction. So this is the spatial direction, right? Epsilon was equivalent to the step size, and u shows us the direction of the update. And you can just find that estimate as this is a norm, right? Norm of u. And you can easily understand, if I want my steepest gradient descent, it's as if I don't want to deduct anything from my epsilon, so u must be 1. So I take into account all of the output of the epsilon in that direction, right? So if the norm of this becomes 1, it's going to be the steepest gradient. So we're going to use all of the epsilon. All right? Okay, so now we have found about the step size and the direction we want to go. Now we need to find out how we're gonna mimic the unknown function of f that we are interested in traversing, right? And that brings us to Taylor series approximation. I mean, there are other methods to approximate that, but one of the well-known methods for gradient descent is applying Taylor series. In general, if you have a function, a known function, say this function, right, f, and this is your x-axis, okay? So there are three methods three possible ways in general to estimate your f prime of j. At the point of j, you want to estimate your f prime of j, right? So one way is to estimate it using the fj minus 1, right? One way is to estimate it from here, and one way is to estimate it between these two. And that will define us three different possible estimates. So the first one is called forward differences, right? So we are here, we are trying to estimate f prime of j, right? So it's going to be equal to f of j minus 1 divided by the distance, right? And the distance is delta x1. So we call this forward difference. On the other hand, if you go backward from fj plus 1, right, with delta x2, you're going to have a backward difference, okay? And there is another one, it's called center difference. So you start from here up to here and you go to the center. That's why you need to add these two as a whole. So delta x1 plus x2, right? Now we know. Now we have some possibilities in order to estimate that. Now we need to apply Taylor series to as a representation of our function as an infinite sum of terms that can be calculated. Okay. I've also uploaded the slides yesterday, so you have them already in Moodle if you wanted to see them. Okay, so let's talk about Taylor series. So we can use Taylor series to derive estimates of derivatives and find their order of accuracy. So this is the, say, the vanilla Taylor series, right? In order to compute fx plus delta x, right, we can expand it to f of x plus delta x f prime of x. So that's the first order derivative. And then we go on the second order, delta x raised to the square divided by 2 factorial f double prime of x. And then we go on and on and on up to the higher orders, up to the last one, right? So in general, in gradient descent, we don't have to expand up to, I don't know, the hundreds, order hundreds or thousands, because if we just use the second one, normally it's good enough for our results, right? But definitely, if you go further and further, and if you expand your derivatives more and more, you have higher accuracy, but it's more computationally intensive for you, right? So, in the case of logistic regression, in order to estimate your fx1, right? So what we can do is like x1 is equal to x0 plus that delta that the unit vector of u and the step size brought us here, right? Thus, we need to compute f of x0 plus step size multiply the unit vector, the gradient of x0 plus the rest, all of those fancy stuff here, right? We call them order, like order x1 minus x0, right? We don't need to compute that because we can just neglect those. By using only this, we are having good enough results, right? We can compute this, that's fine, we know this. So because of that, we can find the f of x. So if you expand the gradient of f of x at the point of x0, it's as if you have df divided by dx1 at point x0 up to d of f. So I'm just talking about the vector of x0, right? It has different x's itself, and all of them are in n-dimensional space of R, right? So as if in in a vector space, right? Normally, it'll show you the spatial direction on the opposite side of your gradient. That's why we need to apply a minus to the gradient in order to have the right direction. Putting all together, our optimal U star is going to be the minimization of the vector of U transpose multiply the gradient of f at the point of x, vector of x0, okay? And that is actually, this is the norm of the gradient, and that's the minus we need to take into account because it's against the direction of that, so the minus of that is going to be the right direction. So to find the U star, we need to just compute gradient and find a norm. Do note that this denominator is a scalar value, right? This is a scalar. Okay. It can be absorbed into the epsilon when we apply later on. All right. So the gradient of x, gradient of f of x0 points in the right direction by applying that minus, right? Where f of x has maximum growth at the point of x0. Does that make sense? So all we need to compute at each of the iteration of the gradient descent is to find, we have already initialized the epsilon, we need to find a gradient of the f of x at the point that we are there, and then find the unit vector that shows the direction towards the maximum growth, okay? Which is the minimum growth, downhill. All right, so let's just summarize it in a pseudocode. So we have the algorithm of gradient descent. We're going to initialize x0. For our iteration from 0 up to the point that we want to stop, we have to compute the gradient at the point at the iteration t, right, of f of xt. And then we find a direction using that gradient. This is going to be the minus of that gradient. This is going to show us the vector of direction. So we call it here v. We're going to update our x. So we're going to start from this point. And we're going to arrive x at t1, x t plus 1, right? For the v of t, that was direction. We're going to update our x using xt plus epsilon and the direction. And we're going to iterate over step 1 until stopping criteria is reached. Shortly, we're going to see how we're going to find such criterion. Any questions? So even though you don't know the function f, you are using the gradient and a step size in order to traverse a space that you didn't know the function of. Okay, so now let's talk about briefly how we're going to find the stopping criteria here. Back to your question. So now we might end up having three different scenarios, right? First of all, and GD stands for gradient descent. So the first situation is when we have multiple stationary points. Okay, we find the gradient of f at the point xt approximately 0. In general, we are hoping that this is a local or global minima, right? But what if the function that we were playing with was in a higher order, right? So it had multiple stationary points. In this case, we have 3 local points. So one of them is global maxima. The others are, one is local minima and the other one is global minima, right? So it has 3 stationary points. It has higher orders, right? So at all these 3 instances, the derivative of x becomes 0, right? And it's going to treat gradient descent. I mean, in the case of the global one, because we were having increase here, we would have known that we are not in the right direction given sort of appropriate the step size. But for the case of x1 and x3, right, on both cases, it's going to trick the gradient descent algorithm on the stop condition. In practice, we have found that generally, most of the local minima are surprisingly good, okay? We might just end up in the first local minima and the results are still good enough for us to accept. If we were not, we can just always reinitialize the points from another place, okay? Is there a question?
Yeah, actually we had a question on the previous slide. So in the 2D step, so VT is the direction.
Yeah.
And ET is the error.
No, it's epsilon.
Is the learning rate?
Yeah, step size.
But like this f is a loss function or have it's a loss function, right? Because we want to minimize our number.
Right.
And that's how we are going
That's
to
right. That's
minimize
right.
our-
Yeah. So this is
the loss function.
yeah. Here. This is a paraboloid of the loss, right? And this point gives us the minimum loss. We are interested in reaching that point, right?
X is the weights, right?
X is
It's the weights that we are needing to calculate.
yes, could be your features, right? In this case, X. Yeah, we have 2 features. Yeah, that's why.
But we won't be able to update our feature. We are going to update our weights, right?
Yeah.
Feature have fixed.
No,
We want to update our
so these are actually the weights of.
weights
yeah.
of the feature.
Yeah, that's right. Yeah. Okay. Good question. Is it clear for everyone?
At global maximum, or maximum in general, you'd only hit that case if you get exactly that, right? There's no way you can reach that?
Here?
Yeah.
I mean, in general, we are not interested in finding a maxima, right?
I know, but if, let's say, your first guess, and it was approximately 0, it's that max.
Right.
That's the only time you'd ever hit it,
Okay.
because your algorithm is supposed to go downward.
Yeah, it's so if on in a rare situation you just find it in the first iteration, normally it is suggested to restart your algorithm with another initialized point, right? So one way that helps is reinitialize your algorithm. Perhaps starting from here, you might start there. Okay. You always hope for finding better points. Okay, so that was the first. Condition. Multiple stationary points. The second condition is when you have a saddle points, right? Still your derivative of f is equal to 0, but it doesn't tell you anything about if this point is a local minima or not. It's actually a turning point because your function has higher orders, right? For instance, if your function was in order of 3x cube, this point still gives you 0, but it's not either a local or minima or maxima, right? So how do we tackle this? Any suggestions?
With the second derivative.
Yeah, this is the easiest way. So in many of the gradient descent algorithm, you have the option just to go on a second derivative, right? So with minor modification, GD algorithm won't get stuck in the saddle point. For instance, we can use the second derivative. Okay? All right. The third stopping condition is, and it's very, very common. You hit a plateau, and there's no way to skip that plateau, right? So how are we going to avoid this? Just like before, either we're going to reinitialize, rerun gradient descent. So we hope that starting from here, perhaps we're going to start there, and we can descend easier. Or we need a larger step size, right? But that's still tricky as well. So these are different remedies that in numerical analysis we use for machine learning, and not, there's no single let's say formula for that. So you need to play. You have to play around with all the tools you have in order to come up with the best solution found. All good? Okay, so let's just combine them all and see what we've known so far. So, gradient descent for linear regression. As you know, linear regression is sort of a linearized version of logistic regression, right? So we can also use gradient descent for linear regression, although it had a closed form solution and using a pseudo, what was the name of that dagger? Pseudo what? What was that?
Pseudo-inverse.
Yeah, pseudo inverse, yeah. I need more coffee. So using that pseudo thing as a closed form, so we are able to find good solutions using gradient descent, okay? Because at the end of the day, if you expand gradient descent for linear regression, it's as if you have 1 over n, the summation of your pointwise errors, right? You're going to expand it to double the transpose xn minus your labels, and you want to minimize this, right? So applying gradient descent to find the next w at the point k plus 1 is going to be this minus your step size of k and the gradient of your in-sample error at the point wk, right? If you expand this, it's going to be wk minus delta of k divided by n, summation of all those point y's here. And at the end of the day, if you just go on forever, you're going to find exactly this. You can easily see in the next slide that if we go on a large n, right, those two solutions would converge to each other. So actually, by having gradient descent, we can converge to that pseudo, what was that pseudo matrix? Yeah, pseudo inverse. So here, now we expand that gradient. So the next update for our w at point k plus 1 is going to be wk minus the step size over the n iteration, and so we are trying to just take the gradient of that, right? 2 comes out, you're going to have double transpose of k xn minus yn, and then as k goes into infinity, you can easily see that this solution converges to this. So you see that even for linear regression, we can use gradient descent as an approximation. So the question is why? Why, when we have a closed form solution, do we need to use an iterative method that might just have an inferior result for us? The answer is very simple in a machine learning board, because if you take a look at the complexity of these two algorithms, gradient descent is a very lightweight algorithm. That's why it's very, very common and popular in machine learning. The order of the computational complexity or the order of gradient descent is just nd, right? However, if you compute the order of pseudo inverse for least square method, or for the linear regression, right? So you had x transpose multiply x, which has the order of nd square. On that formula, here you had here. So you had this, you had an inverse, and you had that. So this one, this dot product is good enough. So order of nd, but the final product is gonna make it d cube. So now between this d cube and nd square, if your n is very, very large, which is almost all the cases, this is the dominant computationally complex sort of fraction of the formula, right? So if n is way, way bigger than d, so the order of complexity for applying that least square method is much, right, higher than gradient descent. And also on the other side, when we are applying linear regression or those linear models in general, if we just go for a closed form solution and just find the exact solution, it's as if we are just overkilling the problem, because the problem wasn't that complex to start with normally. And in practice, when we start a few iterations using gradient descent, we normally see that the loss is decreasing, right? And we can stop whenever we found a reasonable, sort of loss function. Okay? Is it clear? All right, so we're almost done with the linear chapters of our course. I'm just going to wrap up here with this slide. For that credit card application that we saw, on the case of linear classification, we use perceptron, right? It would be either an approve or disapprove, right? Or deny. If we apply the same thing using a linear regression, it was as if we wanted to find the specific amount of credit card that we were, granting the applicant. And on the case of logistic regression, we were interested in finding the probability, right, of that default. So in order to solve that, we were using the learning algorithm for perceptron was either PLA or pocket algorithm or other linear models that are outside the scope of the course. For finding the solution for linear regression, we were using the pseudo inverse within the square, and then the loss function was calculated using square error, right? This was only the classification error. It was either 1 and -1 in the class of binary. And here we compute it as the cross entropy error, that figure that I show. So that was this for each of the points, right? The conditional probability, log lost, and we use gradient descent in order to learn the weights for logistic regression. Starting from next lecture, we're gonna see how we're gonna improve the vanilla, let's say gradient descent, and some other techniques before we start with multi-layer perceptron, which lays the ground for us for neural network. Okay? Any questions? All good? Yeah.
So is logistic regression, like the gradient descent we talked about, it's technically like a numerical descent?
Approximation, yeah. Yeah.
Okay.
Okay. All right. Meanwhile, if you had any questions about your assignment, you can contact your TA as well as me. I've provided the email for the TA in the announcement section of the Moodle, so you can just check that. And you have almost 2 weeks. All right. So see you guys on Wednesday. Have a good day.